Alright guys, let's continue looking at the bond energy as well as that bond diagram we talked about a minute ago. So, we have our bond diagram, and yes, I know it's beautifully straight lines. On the bottom, remember we have bond distance or internuclear distance, which really is equivalent to bond length and more and simpler terms, okay? On the side we have potential energy, so we'll just abbreviate that PE, okay? And remember in the center point, this is zero potential energy, which we define as the atoms being far apart, so that they're not interacting with each other. So this is where one atom's here, another atom's here. We'll shade those in so that this zero over here is a zero, not an atom. Okay, so these guys are as far apart as possible at the 0 point. Again, do they have potential energy here? Yes, they do. We don't actually care what that value is. We define that value as 0. Okay, from there, as these two atoms are coming closer together, they're going to start interacting with each other. Okay, we'll kind of do this little divot. And yes, I know, it's beautifully straight line. Let me try that again. That's a little better. Not much. But you guys get what I'm trying to do. Anyways, we have our lowest point down here, which is where the bond actually forms. This is when bonding actually occurs. And remember, this is technically bouncing back and forth in this range. We call that an average bond length. So the bond length would be kind of down here, where it matches up with our x-axis. Okay, and again, it's an average because it is bouncing back and forth here. Okay, as the atoms get too close to each other, they're going to start repelling each other because the nucleuses get too close together and the electrons get too close together until they have a high potential energy, at which point in time they'll actually fly apart from each other and end up back over in the 0 range. Okay, so what does all this mean? Well, we can actually look at this type of data and determine bond energy, maybe not numerically, but at least qualitatively. But we could determine it numerically if we actually had numbers on our y-axis. So keep in mind, bond energy is actually the difference between here and here. So the 0 point and the bottom of the curve, which is why we really don't care what this number is. We define it as 0, and we're looking at the difference between where we started and where we ended up at the actual bond length. Okay, so what do I mean by determining bond energy qualitatively? What I mean by that is the deeper this curve is, meaning the farther down it is on our potential energy scale, the stronger the bond is. Because remember, this is potential energy, and we end up with negative potential energy because it's below 0 here, which means it's just lost energy. It's lost potential energy. And remember, a loss of potential energy basically equivalates back to stability. Okay, the more loss of potential energy a bond has, the more stable the bond is. So if we think about a single bond, a double bond, and a triple bond, well, which one of these is going to be more stable, assuming that they're occurring between the same atom? So let's say we're looking at a alkane, which is a single bonded carbon-carbon, alkene, double bonded carbon-carbon, and an alkyne, triple bonded carbon-carbon. So same atom all the way down. Okay, so we're not looking at force of attraction due to a difference in atom size or anything like that. They're all the same atom. We're just looking at the force of attraction due to the amount of bonding that's occurring between them. Which one of these is a stronger bond? Well, it's our triple bond. Okay, and because it's stronger, that means it is actually more stable. It's a more stable bond. So what does that mean in terms of potential energy? It means the curve for this carbon triple bond is going to be very, very deep. It's going to be down low here, meaning it lost a lot of energy to form, or it released a lot of energy when it formed, which means it's going to end up with a higher bond energy. So remember, we talked about bond energy being kind of an absolute value. So if we go back over here and look at these values, these are absolute values, and really what it comes down to from where this started, so the carbon-oxygen, where they started being far apart from each other, and where they ended when they were chemically bonded together. So the 745 would be somewhere down here, okay? Versus if we go back to the 413, our weakest one in that case, oh, there we go, it would be higher up here. It lost less potential energy than the carbon-oxygen bond. Well, why? Because it's a less stable bond. Carbon and oxygen is a more stable bond. So that's kind of looking at this qualitatively, and the reason I'm showing you that is that's very common with our multiple choice, or can be common in the multiple choice section. So let's just kind of look at a problem. Okay, and forgive my drawing here. I will do the best I can. Let's say we have one of these graphs, and on these graphs we have 3 different bonds. Okay, or we have 3 different atom bonds that we're looking at. We've got one that goes here. We have one, and actually I need to redo that. You'll see why in just a minute. It's going to go here. There we go. We're going to have one that does that, and we're going to have another one that does that. And we're going to call these X, Y, and Z. And let's say we're looking at diatomics of fluorine, nitrogen, and oxygen. So let's say we're looking at those 3 atoms, or molecules, okay? So the first thing I want you to do is draw the Lewis dot structure for all 3 of these. So pause real quick, draw the Lewis dot structures, and stop right there. Okay, so if we're drawing the Lewis dot structure for fluorine, we end up with fluorine single bonded to fluorine, with, yes, both of these having a full octet. We end up with nitrogen triple bonded to nitrogen, with a full octet being 2 more electrons on both of these, and oxygen being double bonded to oxygen with 4 pairs of electrons, or 2 pairs of electrons, sorry, on both of them, okay? So 2 things I want us to make note of here. The first thing we have to pay attention to is atom size, okay? How would you compare the size of fluorine, nitrogen, and oxygen in the grand scheme of things? Is there a significant difference due to energy levels? No. So we're going to say they're all similar size. Okay, all similar sizes. The next thing I want to do is pay attention to the types of bonds. Well, we have a single, a double, and a triple. What does that mean? Single is just 1 sigma bond, double is a sigma pi, and the triple is a sigma and 2 pi. So we go from our weakest, middle ground, and our strongest of these 3. So if we wanted to know which one of these, X, Y, or Z, is which one of these guys, if we wanted to label X, Y, and Z based off of these guys, we can use this information of type of bond, meaning double, single, or triple, okay, as well as the atom size to really make that determination between these. So, first thing I want to do is look at X. We have bond length on our x-axis, and we have potential energy, our bond strength, on our y-axis. X is going to be our shortest bond, okay, because notice where it is. That's where our X is, where our Y is, and where our Z is. So Z is our longest bond, X is our shortest, Y is in the middle. We then have bond strength being here, which is the bottom of the curve. Okay, and that means X is going to have the strongest, Y is going to be in the middle, and Z is going to be our weakest of our 3 bonds. Okay, so what does that mean? First and foremost, let's talk about bond length. Let's look at that. X is our shortest bond length. What do you remember about single, double, and triple bonds? Well, you should remember sigma by itself is our longest bond. As we add a pi bond to make a double, it pulls everything closer together, so this is our kind of middle of the road. And then if we add a second pi in, that's going to make it even shorter. So remember, as we increase the amount of bonds, we are shortening the bond length. So our nitrogen is going to be our shortest. Okay, oxygen is going to be in the middle somewhere again, and fluorine is going to be our longest. Okay, which means chances are what we're looking at is Z is probably fluorine. Okay, Y is probably oxygen, and X is probably nitrogen. Now, before we finish that up, let's double check that and see if that makes sense according to our bond strength as well. Because that's really what I'm wanting you to look at, is the bond strength, not so much the bond length. Bond length can be a little bit interesting when you start looking at things that are on different energy levels, because then you have atom size you have to take into consideration, not just the type of bond. But in this case, the type of bond does make it very, very easy. Okay? But let's talk about bond strength. So X is our strongest bond. Well, which one of these 3s is our strongest? It's our triple bond. So does it make sense that X, being the shortest and the strongest, is nitrogen? Yes, it does. Y is in the middle of the road, okay, and that's our oxygen. So it's got kind of that middle of the road strength, and it's kind of got the middle of the road length. And then our weakest bond strength is Z, and it's also our farthest apart, which again should come back to our Coulomb's law concept of force of attraction, Q1, Q2 over radius squared. As these get further apart, our force of attraction gets weaker, therefore our bond strength gets weaker, and vice versa. As this gets smaller, let's say with our triple bond it gets smaller, force of attraction increases. Okay? Okay, so this is a type of question you could expect on both the short quiz and the test. Okay, different compounds or different types of bonds, but the same type of basic question. Okay, another type of chart you could see is something like this. Okay, this is a potential energy curve for a chemical reaction. So keep in mind, this is looking at the potential energy curve for a bond. This is looking at the potential energy of a reaction. Okay, and there's two different types, or actually it's the same type, but they look a little bit different. So this is for an exothermic reaction. Okay, and how do I know it's exothermic besides the fact that it happens to say it right here? What I want you to notice it starts with a certain amount of potential energy, and it ends with a certain amount of potential energy. What do you notice about the difference between where it starts and where it ends? It starts at a much higher point, ends at a much lower point, okay? So what happens to this potential energy? Well, it gets lost, and it gets lost as heat, or kinetic energy, what we can measure. Okay, and what we're actually looking at is the potential energy the reactants have and the potential energy the products have. And again, this is on average, so we're looking at the total or average potential energy of the reactants and the average potential energy of the products. So what I want you to notice, the potential energy of the reactants is higher, meaning they have more potential energy, and the potential energy of the products has less, or it's a lower potential energy. So think back to what that means. Potential energy can tell us about stability, our strength, and technicality. Okay? So if the reactants have more potential energy, that means they are less stable and therefore are weaker. Okay? In terms of the products, they have less potential energy, which means they are more stable and they are stronger. And again, this is on average. On average, the bonds of the reactants are weaker than the bonds of the products. So what that means is energy goes in to break bonds all the time. Period in the story. Bond breaking always requires energy, okay? And a reaction is always going to require us to break these bonds first before these bonds can be formed. So energy goes in to break these bonds, and then when the new bonds form, they release energy. Okay, so think back to our little chart thingy, okay? And I'm kind of oversimplifying this, but let's say this is our reactants, but this is our products, okay? So energy goes in to break the reactants bonds, and energy goes out when the products form. Notice what happens here. The little bit of energy that's used is a lot less than the amount of energy that is released. So what we end up with is a net energy release. Okay, therefore we end up with a negative delta H and an exothermic reaction. So what do I want you to gain from here? What I want you to understand, first and foremost, is that an exothermic heat curve looks something like this, or not heat curve, sorry, potential energy curve, bonding curve, looks something like this, where the reactants are higher and the products are lower. What does that mean? That tells us the average strength difference, and it tells us that the reactants are overall weaker bonds, and the products are overall stronger bonds. Okay, and that tells us that energy is being lost and therefore exothermic. Now, if there were numbers on here, like let's say this was 50 and this was 20, we could then determine that 30 kilojoules or joules, whatever it happens to be, were lost. Okay, now right now we're looking at this more qualitative than quantitatively. Okay, so that's what I want you to get at right now. We'll come back and talk about endothermic in just a moment.